Welcome to the next lecture of polymer reaction engineering. Here we are going to discuss with the various temperature dependent terms and interpretation of various kind of batch reactor data. So let's have a look about what we have studied previously. So we had a discussion about various approaches of reactor design. What are the integral components involved in the reactor design? What are the rate law? What are the different type of a reaction? What are the rate equations, etc. Now, in this lecture series, we will discuss about the concept of temperature dependent term. We will interpret the various batch reactor data available during the course of time. We will have a brief outlook about the conversion, concentration and mole balance concepts. We will discuss about the system pertaining to the constant volume reaction approaches, and then again we will come back to the rate of a reaction, especially emphasizing to the first and zero order reaction, those who are attributed to the polymer synthesis or polymer reaction. So let's have a first thing related to the temperature dependent term. Now, as we agree upon that the temperature plays a very vital role in the reaction design or reactor design, and there are so many type of reactors which we had already discussed in the previous lecture, and everywhere you find that the output is usually dependent on the temperature. So there are various laws, they are embedded in this temperature dependent term. One is the Arrhenius law. It's a very well known law and a very common law. Now this law suggests a formula for the temperature dependency of any kind of reaction rates. So we discussed these reaction rates in the previous lecture. Now here this temperature dependency is tutored by this Arrhenius law. Now the integral part of this Arrhenius law, that the specific rate constant, usually denoted with the help of a small k, is the only term which is a temperature dependent term in the rate law. So according to Arrhenius law, a specific constant, whatever specific constant, this can be defined as k is equal to k naught e to the power minus e RT. We had already discussed this particular equation. Now here this k naught in this previous equation, k naught represents the frequency factor or pre-exponential factor and having the same unit as the specific rate constant k. Now this equation is fitted experimentally over the wide range of real temperature profile. Here E is the activation energy and usually represented in the unit of joule per mole. R is universal gas constant, and the value is sometimes referred as 8.314 joule per mole Kelvin, and T in this particular equation is in the temperature, absolute temperature, and represented as K, that is Kelvin. Now for two different reaction temperature, if they are having the same concentration of reactant, this equation gives a different type of equation which we are going to discuss, which is helpful to calculate the unknown reaction temperature, rate of the reaction and a specific rate constant. So when one of them is usually given, so let's have a look about this particular approach. Now according to Arrhenius law, we are having k is equal to k naught e to the power minus RT. Now for temperature T1, K1 is equal to k naught e to the power minus RT1. Now if we take the log of both sides, then this equation becomes K1 is equal to ln k naught minus E upon RT1. This is the equation number 1, let us say. Now for temperature T2, this equation becomes K2 is equal to K naught minus E upon RT2. Now, again if we take the log, then this ln K2 K naught minus E upon RT2. So, this is your equation number 2. Now, if we subtract this equation 2 from equation 1 and if we rearrange the things, then we will have ln K1 upon K2 is equal to E upon R 1 upon T2 minus 1 upon T1. This is equation number 3. So, as rate, say Ri is a function of, we have discussed this thing previously, function of temperature, composition. So, Ri is equal to K F2 composition, or Ri is proportional to K. So, therefore, ln K1 upon K2 is referred as E upon R 1 upon T2 minus 1 upon T1 R1 upon R2. So, this is you can say your master or generalized equation referred as equation number 4. Please try to remember this particular equation because we will utilize this equation thereafter. So, now if we draw the graph showing the temperature dependency of a specific rate constant in between ln K versus 1 upon T. So, usually the graph is straight line with the slope of E upon R. So, here we have plot this one. Now, if we are having the low activation energy, then the slope would be represented as E upon R, and if we are having the high activation energy, then it is represented like this. So, let us interpret this thing in a sequential order. Low slope with low activation energy. This is the low slope with the low activation energy, and it represents the high slope with high activation energy. So, the reactions are high temperature sensitive with the high activation energy, and a low temperature sensitive or insensitive with low activation energy. The reaction are sometimes more temperature sensitive at low temperature than high temperature, and the value of the frequency factor is sometimes temperature insensitive. Now, people tried to develop this particular approach with the help of a collision theory, which we discussed in the previous lecture. It is usually based on the kinetic theory of a gas, and it is falling for unimolecular reaction. Now, according to the collision theory, the specific rate constant K you can always describe as K is equal to T to the power half K naught E minus upon RT. Now, for say T1, K1 is equal to T1 half K naught RT1, or ln K1 is equal to half ln T1 plus ln K naught minus E upon RT1. You may refer as equation number 5. Previously, we discussed the equation 4 equation. For T2, K2 is equal to T2 RT2, and ln T2 plus ln K naught minus E upon RT2. This is equation number 6. Now, upon subtracting equation 6 from equation number 5, we have ln R1 upon R2 is equal to ln K1 upon K2 is equal to 1 upon 2 ln T1 upon T2 plus E upon R T2 minus T1. Now this is again the generalized equation, and you may refer as equation number 7. So by this way you can see that how this rate constant or a rate of a reaction depends on the temperature factor. Now another theory which put forward with the help of to help the temperature dependency term, that is called the transition state theory. Now this theory particularly explains the reaction rate of elementary chemical reaction. If you recall that in the previous lecture we discussed about the elementary reactions. Now this theory assumes a special type of a chemical equilibrium that is called the quasi-equilibrium, this between the reactants and activation transition state complexes. Now according to this particular theory, the specific rate constant have the relations like this. Now let us have a look about this relationship to transition state theory. Now K is equal to T K naught. Now for T1, this K1 is equal to T1 K naught e to the power minus RT1, or you say that ln K1 is equal to ln T1 plus ln K naught minus E upon RT1. Let us say this equation number 8. Now for T2, K2 is equal to T2 K naught. Now remember our reactor operates in between T1 and T2. So K naught e to the power minus RT2, or ln K2 is equal to ln T2 plus ln K naught minus E upon RT2. This is equation number 9. Now if we subtract this equation number 6 from 5, similarly we will have equation number 9 to 8, then we have ln K1 K2 ln T2 upon T1, this is T1 T2 plus E upon R. Now as rate is directly proportional to rate constant, this gives you ln K1 upon K2 ln R1 upon R2 ln T1 upon T2 plus E upon R 1 upon T2 minus 1 upon T1. So this is again one of the generalized equation, and this we can say this is the equation number 10. Now sometimes we need to refer to the conversion aspect, and this conversion aspect is again a very important part, because ultimately it decides the various factors attributed to the economics of the reactor, economics of your polymerization process. So let's have a brief look about what is conversion. It is referred to the fraction of any reactant, suppose A. It is converted to the product, and suppose a reactant A in a reactor having initial moles of Na naught at time t is equal to 0. That means at the startup, and after some time t, the moles of reactant A remaining in the reactor are say Na. So the initial moles of reactant A in the reactor are Na naught, and the moles of reactant A converted into product or any kind of a reaction, they are Na naught minus Na. Now, then the conversion of reactant A can be expressed as the ratio of moles of reactant A converted after time t to the initial number of moles. Now, sometimes mathematically we can represent this equation like this, that is the conversion of reactant A, that is sometimes referred as XA, is equal to Na naught minus Na upon Na naught. For reference, we may cite this equation as 11. Now, the moles of reactant A converted and that is they are referred as Na naught minus Na is equal to Na naught Xa, and the moles of reactant A remaining within the system, they are Na naught 1 minus Xa. This is referred as equation number 3. Now, sometimes it gives an important information pertaining to the unreacted segment of reaction mass. That is why this particular information is extremely useful, specifically for the separation process, specifically for the product purity, etc. Now, another thing which is very important related to the batch reactor interpretation of the batch reactor data, that is the mole balance of a batch reacting system. Now, suppose a chemical reaction take place in a reactor with the moles of reactant A and B, right. So, the corresponding you can say the stoichiometric number are small a and small b, and they are by reacting with each other, they are forming the product C and D with the corresponding stoichiometric number C and D. So, we can arrange this equation, which is the following equation, on taking the reactant A as a limiting reactant, and this equation can be modified as A plus B upon A B, C upon A C plus D upon A D. So, here the previous chemical equation, and if you take the cognizance of the previous chemical equation, for every 1 mole of reactant A, the B upon A mole of reactant B are consumed, that is why you need to put the negative sign over here, and C upon A moles of product C and D upon A moles of product D are formed. So, usually you can say the moles of reactant B consumed is equal to B upon A moles of A reacted. Now, if in other words we say that if N naught and B naught, this represents the initial moles of reactant B, and B represents the moles of reactant B remaining after time t, then you can with the help of this previous equation, you can represent that moles of reactant B converted, that is NB naught minus NB, which is equal to B upon A Na naught Xa, or B upon A, that is the converted moles of reactant A. So, the moles of reactant B remaining in the reaction mass, that is represented as NB, this can be represented as NB is equal to NB naught minus B upon A Na naught Xa, and you can write this as equation number 14. So, now, because see when A and B both are consuming in the reaction mass, then we have to look that about the efficacy of the formation of product C and D for every mole of reactant A. Now, this can be represented as the formation of C. So, formation of the product C that is number of moles of C. Initially, maybe if initially there is no mole of C present, then always you can put the numerical value equal to 0 plus C upon A Na naught Xa, that is the equation number 15. Now, similarly you can write for product D, that is Nd is equal to Nd naught plus D upon A Na naught Xa. This is the equation number 16. Now, here the addition term in this these two equation, that is the formation of product C and D from the stoichiometric consumption of reactant A. Now, if the total initial moles present at the start of the reaction at time t naught is equal to 0 is represented by Nt naught, then we can write this generalized equation Nt naught is equal to Na naught plus Nb naught plus Nc naught plus Nd naught plus Ni naught. This is if represented that if inert is present in the reactor. This is a very common thing. Sometimes you need to put the inert in the reactor to make the shift of reaction, and these inerts are not converted into the product. So, total number of moles at time t moles after time t, let us say they are equal to Nt. So, Nt is equal to Na plus Nb plus Nc plus Nd plus Ni. Now, if we expand this thing, then you can represent like this. Again, I am writing back to this equation Na plus Nb plus Nc just for the ease of explanation. Now, this is Na naught plus, sorry, this is related to the consumption. So, Na naught Xa plus Nb minus B upon A Na Xa plus Nc naught plus C upon A and A naught Xa plus Nd naught plus D upon A Na naught Xa plus N initial concentration. Now, Nt is equal to Nt naught plus Na naught D upon A plus C upon A minus B upon A minus 1 Xa. Now, this is Nt is equal to Nt naught plus, let us say that this is a change Na naught Xa. Now, this reflects the change in number of moles per unit moles of A. So, this particular equation is again a very crucial equation related to the conversion aspect, and it is a very useful equation. Let us have a brief look about the constant volume reaction system. Now, it means the volume of a reaction mixture and not the volume of the reactor is constant. So, that is the constant density reaction system. So, this relates to the constant density type of system, like all fluid phase, all liquid phase reactions and all gaseous phase reactions are occurring in the reactor of constant volume. Now let's have a brief look about the concentration aspect in this kind of a reaction system. Now let the initial volume of a reacting fluid at time t naught is equal to 0 be represented as V naught, and the initial number of moles are Na naught be then the concentration of the reactant A can be described as it is the ratio of moles of reactants those who are dissolved in given volume of the reacting mixture. Now, this can be represented as the concentration of reactant A, the concentration for reactant A can be written as at T is equal to 0, that is Ca naught is equal to Na naught V naught. Now, the concentration of reactant at any time t, this is equal to Ca Na upon V. We described this V previously. Now, for constant volume system, this V is equal to V naught. So, Ca is equal to Na naught 1 minus Xa upon V naught, or Ca is equal to Ca naught, because this becomes this one concentration term, Ca naught 1 minus Xa. So, this is this equation represents the concentration of reactant A to the system. Now, the concentration and conversion, these two things are very important related to the reactor data. Now, this can be clubbed, or this can be related to each other like these equations. So, let us have this particular approach. Cb is equal to Nb upon V, Nb naught minus B upon A, as V is equal to V naught. Now, C, concentration of C component, that is Nc upon V, is equal to Nc naught plus C upon A. Cd is equal to concentration of component D is equal to and if we talk about the total concentration, then it can be represented as Nt upon V is Nt naught Na naught Xa upon V. So, these are the concentration conversion terms you can be related, and to be more precise, if we go for this concentration conversion term again, then Ca is equal to Ca naught 1 minus Xa. Here Xa is equal to Ca naught minus Ca upon Ca naught, or Xa is equal to 1 minus Ca upon Ca naught. Now, if we differentiate the both side, then it can be represented like minus dCA upon dCA naught. So, this is the generalized equation. So, in this particular lecture, we discussed about the various factors associated with the interpretation of different kind of batch reactor data, apart from other factors which are embedded for the designing of reactor concept. Now, by this way, I am summing up this particular lecture, and we will continue about the rate of a reaction and other parameters associated with the batch reactor design in the subsequent lecture. Thank you very much.